Now this slide is showing you a typical embedded system targeting the PowerPC 440 processor core. Note that first of all, since we're using the PowerPC 440, we must be targeting the Virtex 5 FXT family. In this situation, there are 4 buses in this design. There are 2 PLB V46 buses in this design. The PLB V46 bus standard is designed for high speed and high bandwidth peripherals. It supports 128 bits of data and 36 bits of address. It also supports dynamic bus sizing and a programmable burst size. As you can see, one of these buses is connected to the master port of the PowerPC 440, labeled the MPLB port, and the other is connected to the slave port, labeled the SPLB. The master is designed to give the processor faster access to the peripherals attached to it, in this case, a generic high-speed peripheral. It also has an external memory controller and a gigabit Ethernet controller. The memory controller can be customized to support zero-bus turnaround, or ZBT, a double data rate, as well as other memory components that you may use. Often customers will ask how fast the embedded system can run. Now that will depend on the processor and the number of peripherals on each bus. Specifically, how many LUTs and registers are required for each peripheral on each bus will determine how fast each bus will run. Since the PowerPC 440 is a fixed ASIC, its performance is guaranteed. The 440 supports multiple clocks in its embedded system. In this case, the master PLB will probably have a separate clock domain from the processor as well as the slave PLB bus, and their speeds will depend on the amount of logic for the associated peripherals. But since we are attaching a lot of IP to the master PLB, its speed will depend on how many FPGA resources are attached and can only be predicted after implementation of the FPGA. That's because place and route will have to be completed before the true timing information will be known. The slave bus is designed for the connection of other master peripherals. In this case, another bus master may want access to the peripherals in the system. Most commonly, the peripherals on the slave bus, since it would provide faster access. The master bus should only have slave peripherals that only the PowerPC is going to need access to. The 440 also has a dedicated memory controller port, or MCI port, that speeds data access since it is 64 bits wide. However, it is designed to only support the DDR2 memory standard. The 440 also supports direct memory access through a 32-bit DMA port. This is frequently used by Xilinx customers who use the dedicated TMAC core that is included with many of Xilinx's FPGAs. Note that EDK provides all these peripherals, which are all free. There are some peripherals that have a charge associated with them, but they are very sophisticated and would take a designer a great deal of time to replicate. And frankly, they're probably not as mainstream as you might think. All the mainstream stuff is free. These are described and supported through the same EDK software and the IP documentation if you want to see what is included. Now, after looking at that last PowerPC system, we'll point out to you MicroBlaze systems are usually simpler because MicroBlaze only supports 2 bus standards, the PLB V46 and the Xilinx Local Memory Bus Standards, or LMB. The LMB is designed to interface only to local FPGA block RAMs. You should also note that MicroBlaze does not include any cache resources by default. When activated, MicroBlaze will implement cache with block RAMs. There is also support for a fast simplex link, commonly called an FSL. The FSL is designed to offload computationally intensive functions to the FPGA fabric, such as a large multiplication or large math function that might be completed more efficiently within a DSP slice per se. By delivering the multipliers to the logic and then routing the solution back to the MicroBlaze core, we save cycles of execution on the PLB bus and use minimal logic resources because the DSP slice resources are dedicated in silicon. Now, the FSL simply constructs a FIFO and routes the signals appropriately to and from whatever logic is attached to the other end. The MicroBlaze processor also includes a tightly coupled off-chip flash SRAM memory controller interface to provide high-speed, low-latency access called a cache link. The cache link interface implements the cache function without tying up the PLB bus. This is similar to the fast simplex link. This diagram also shows a pretty typical application that uses not only a MicroBlaze processor, but also a 440 processor. In this case, the PowerPC 440 system has its own PLB master bus and also has a shared slave bus that is also connected to a MicroBlaze core. This is done so that the less time-intensive functions can be offloaded to a separate processor. In this example, that might be the MicroBlaze processor. Now don't forget, MicroBlaze again is a soft processor core, which means it uses standard FPGA logic, thus it can target any of our FPGAs. Now, as I mentioned, there is a lot of IP included within EDK, and these apply for both MicroBlaze as well as the PowerPC 440 processor systems. Now, almost all of this is free, and in this case, all of this mainstream cores we're seeing right here are all free. And these, of course, include bus infrastructure and bridge components, memory and memory controller cores, there's debug cores, there's, of course, standard peripherals such as UARTs, arithmetic functions, timers, interprocessor communication cores, external peripheral controllers, a DMA controller, a PCI core, as well as user core templates. So in the end, you're going to have to open the tools and go find these cores from within the library to determine if there's a cost. I'm pretty sure the PCI core, there'll be a charge with it depending upon its size and functionality. But I think all the others are free. So now that we've kind of given you an introduction to what a typical hardware embedded system would look like, now we're going to get into the overview of the EDK toolkit. Now, EDK is a software suite that contains the essential utilities customers need to build their embedded system for a Xilinx FPGA. It has tools, documentation, as I mentioned, IP, that is IP for peripherals. It also provides a software construction environment called SDK for Software Developers Kit. That is an Eclipse-based software design environment. This uses the GNU Cross Compiler, which is the industry standard, and drivers for each of the peripherals included within EDK are, of course, provided. The tool set includes a software debugger to enable software testing on hardware and a model generator to support hardware simulation in a standard HDL flow as well.